Good day to you. This is Galactic on the 28th day of November, a Friday. I hope you're looking forward to the weekend, and no better way to kick it off than with some science. Now, this is the third in our series on circular mathematics. We did cover the number system, which you can see here on the whiteboard, and if perhaps you're viewing this on a cell phone, I will simply tell you what's there. The number system that we've used for well over 2,000 years is displayed here. You can see numbers. There is a 1, and it's in many places. There's a 2, and there is a 0, but the 0 is only in one place. I will use my organic pointer here to show you that 2 to the 0th power equals 1. There is a proof for that. When I first saw that, and I know I remember vaguely that I wasn't the only one in the class that had a question about that. Is that natural? We can make the power series on the base 2 system, which simply means that 2 is the number that's being affected by the power number, traditionally notated as a superscript number. 2 to the first is 2. Any number to the first power is itself. 2 to the second power essentially is described as meaning 2 times 2, which would be 4. But 2 to the 0th power needs some explanation. And there is a very good explanation for that, which I'd like to impart now, because this is the number system that's used on the plane when the plane is not Euclidean. It's the only other possible geometry besides Euclidean if you want a metric. Anybody can draw a triangle or a square or any other shape and do whatever they want with it, but you cannot make a geometry except, first of all, the way Euclid did, which makes a one-component number system, which may seem redundant until you examine what happens if you make a circle instead of a line. That is a closed line. That's one way to say it. The circle that you see here would then have a value that would have to be composed on two linear numbers, because linear numbers are the ones we use. We really can't get away from that. There is no other way to metricize distance than with single component numbers beginning at 0. All of that has been proved, and I trust you accept that fully. Now, what that means is we are intending to use linear numbers in a new way. The way that Euclid constructed linear space was first by describing a point, which we would say today is a zero-dimensioned point, essentially meaning it's not even there. But it does gain a retroactive definition as a position in space if you just have a point, which is exactly how Euclid began his famous book Elements, was saying that a point has none of the three linear dimensions, which he called length, breadth, and height. So those are the three dimensions. He did not use the number 3, and he did not say it was 3 dimensions. But that is exactly what he said in his own way. So we all have accepted that, and everybody has heard the term 3D space. That does make physiological sense, so there's no arguing with that. But the uptake of this 2,500 years of consistent use of linear mathematics is based on Euclid's linear geometry, which should be briefly described. If you already know this, it never hurts to go over this, because this is the basis of science right here. The axiomatic basis of both geometry and mathematics. In mathematics, we begin with numbers. In geometry, we begin with objects. What Euclid began with, therefore, would have to be called an object, and it's an interesting object because it doesn't really have much meaning. The way he axiomatized it, as an object that essentially is not there. Because if it doesn't have any dimensional, you can fill in the blank, it doesn't have any dimensions, well, it's not really there. Now, we can adjust in our own minds and realize that that's not really a problem, as long as you can define later what that point actually will mean. And there is a word for that that's extremely simple but extremely powerful. It is called a position. So in this diagram, you see that the circle does in fact have a position because it has a point at the center. Now that's a very interesting point. So I would like to describe it in the way that we developed over the past 2,000 years essentially. Is that a number? It will have to be, but we also will need to prove that, just to be sure that we're not making any mistakes, because a lot rides on what we do next. You see that I've drawn a circle, but you also see that I have not drawn a y-axis, nor have I drawn an x-axis. And yet they are there. And that is called superposition in its most elementary geometric form. A case example thereof, which is you have a space, which is the plane, and then you have your first object, which is a point. We're just going to begin the way Euclid did, and there is the point. And then he defined the line, which is one dimension of points. That's rather significant, and we're not going to press that, because you don't have to say that. You don't have to say that the line is made of points, necessarily. Oh, what law is there that you've ever read that says when you draw a line, it must be made of points? Well, I should say you're quite presumptuous. And so we're simply being cautious here. We have a space, which here is the plane, which means that it's not volume space. Is there any space that's less than the plane? You know that there's a space greater than the plane because all you do is add a third line whereby you can expand the plane. And that will make what is called volume space. It's not given a specific name when your approach matters this way. But if you began with 1D and you then made 2D, what does that mean? It means you drew a second line. Not quite. Because as you can tell, once you draw a line, you are defining the line that goes through that point. That's just a premise. That's the way Euclid did it. If you have a point, you can make a line. So it goes from 0D to 1D. And that goes to two infinities, which you also don't have to say. And in fact, if you're using the line the way men used it for 2,000 years, it is not going to infinity. It is going a distance. So we metricize the line with numbers in order to compute distance. And of course, you know, you measure the distance with something like a string. But what you want to do is measure all the lines, for instance, on your plot of land or on your large piece of stone that you want to cut to fit your pyramid. You want to be sure that the same metric you use on one line to measure for whatever you need to measure that line for, you want to use the same metric for all the other lines. And if you do that, you can use mathematics. Now that brings us about to the second grade, I should suppose. And so we're going methodically, but now things get hairy because we're in the 21st century now, and we've still been using that same number system, which nobody has ever questioned. It can be proved that you must begin with a linear metric for a line if you want to get computable numbers, which I find a remarkable statement. The reason is the linear numbers are single component numbers. When you have a 1, you don't have any muss or fuss. That is, we would say to begin with, 1 apple. It's a counting number. Now, in the case of distance, you're not counting apples. For one thing, apples are not all alike, unless perhaps you're treating them as if they were all alike. For instance, they all have the same price. So we do use numbers to count money, monetary units. Not quite the same thing as distance, but it uses the same numbers, and those are counting numbers. We're only going to talk about counting numbers for now. One of the reasons for limiting what we mean by number is because we can, at first. Because that really is how Euclid's system develops naturally. The first thing that the line is used for, certainly in history, but really all through history, is to measure distance. Distance has a much more specific term, which I prefer to use, but I'm only going to mention it once because it's 3 words long. Technically, it must be called linear, referring to the space. Linear, spatial, so you're not talking about time, for instance. You're not measuring time, you're measuring space. So why is the line called a space? Technically, it's a subspace. But geometrically, the word space is used differently than it's used to describe physical space. So space is an enormously confusing word. You're going to find out that every term, such as point and line, are extremely confusing if you let it. I won't let that happen. That's one of the tremendous advantages of expending the extra time, and really to try your own patience perhaps, to go through a proof sequence. That's what this is. This is actually a proof sequence for what I'm going to show you, which if you've looked at the previous 2 videos, or even the last one, you know that I'm attempting to establish something brand new in science, something brand new in mathematics, something brand new in geometry. And in this continuing series, as we go forward, it will be a brand new approach to physics at some surprising levels. So this is what I would consider to be significant and worth knowing about, even if it's eventually shot full of holes and it sinks. I've ensured to the best of my ability that that cannot happen through the use of rigorous proof, which is called science. So, what we have here on this whiteboard is essentially the same thing you see in this inset window, a circle. And there are no straightnesses anywhere when you draw a circle. So it's a peculiar object, and you can see that it is in fact the simplest of a certain kind of shape. We won't go into the details of what we mean by shape or anything like that, because I believe most of my listeners are advanced enough in their education to know what a circle is. But now we need to be a little more precise, because we need to know how to use numbers on lines. We have mastered the art of distance. The extension of the use of numbers for an object in this case the line, can be extended to another space which is one dimension higher than linear space. The line must be considered an object because you can see it. So technically you can call it an object. It sounds a little strange to someone who's not well versed in geometry to the level that becomes a comfortable thing to say. And this has to do with the incredible confusion caused by using the word space in more than two ways, but we've already exposed two of the definitions of space, one of which is physical space, but a geometric space has a different definition. In this case, we're saying that the object called the line exists in a space, and we don't necessarily say that that space is space. But if you do say that that space is space, then you have spatial space. You do have to be very particular, especially when you get to space-time, because one of the dimensions is not space. So this is a very good way to begin to accustom ourselves to the concept of space in two rather different views. Now, geometry has as its aim to match physical reality, and taking a straight line distance on the surface of the Earth has proved enormously useful to us. This can be extended, of course, to any surface such as wood or stone or any other. You would want to engineer something, you would probably want to take measurements first for accuracy. The metric of the space is the application of numbers. That can also be called the parameterization of the space, and that's more of an algebraic term. Now, I don't mean to confuse you. We're going to keep this simple, but I want you to be aware that this is a synthesis sequence, which is rather difficult to say. I shall try to say that again. A synthesis sequence, which means we're putting things together that we already know. And we're actually putting them together in a slightly different way. How so? Can I state briefly? Yes, it will be non-Euclidean, and that's technically correct. So this is the world's first non-Euclidean geometry. There's a footnote. Because of the work of Bolyai János in Transylvania, which at that time was in the Austro-Hungarian Empire, but it's really in, I believe that is Romania, or Romania, depending on how you spell Romania or Romania. But Bolyai János, János is his first name, but the Romanians put the last name first. I've never seen that done anywhere else except in Japan. But I'm not well versed in that kind of, there may be other languages that do that. But we would say János Bolyai, whose father was in touch with Gauss, who was the top mathematician in Europe at that time, as you are probably aware, and you would then be able to identify, if you do know Gauss, when that was, which was the first half of the 19th century, which we still use, and I still use. It's actually the 1800s. There's a mathematical reason why the 1800s are the 19th century, but I won't go over that now. It is approximately the early 1800s that János Bolyai discovered what was called later, and still is called, non-Euclidean geometry. That is a distinct misnomer. No, it's not non-Euclidean geometry. What it is the use of Euclidean geometry to violate the parallel postulate. And that was done in two essentially inverse ways. Because the parallel postulate, which is a very interesting postulate that Euclid seemed to just throw in for some reason. And that has been discussed. If you're very interested in the parallel postulate, you're on a good track, and get all the information you can about it, although it will overwhelm you eventually. It gets down to some really amazing distinctions. Because if you have two parallel lines and you extend them to infinity, you run into a monumental paradox, which can be stated in several ways. So the reason why Bolyai and also Lobachevsky, whom I will get to in a moment, a simultaneous discovery, actually quite frequent, more often than you would expect. Nobody knew anything about non-parallel postulate Euclidean geometry. It was a violation of the parallel postulate to invent that kind of geometry, but it's still linear. And I'll show that to you so that makes perfect sense. And then you'll be a know-it-all. And you could use that power to overpower lesser beings who think they know something about, non-Euclidean geometry. You could catch them. But you know what? It'll take you as long to explain to them as it probably will take me to explain it to you. So, leaving aside the niceties of the postulate, which I think you can imagine why. Having two what do you mean parallel? How do you know they're parallel? It's very interesting to try to answer that, and dozens of people over the centuries have tried to get at that. To show whether it even belongs in Euclidean geometry or not, it seems extraneous. But nobody was ever able to solve that. But yesterday, if you watched that video, I solved it for you. It's actually easy to solve once you know my geometry. And it's simply the circularization of the plane rather than the linearization of the plane. But then that requires some elaboration, some more information, because that doesn't really completely say anything. So what do I mean that the plane can be parameterized? Well, the plane is, of course, a planar space. You will often hear that the plane can be considered an object. No, it can't, but it does depend on how you define these two terms. I have determined the correct way to define both terms so that there's no ambiguity. The plane cannot be called a space because of this funny-looking number, which is sometimes called lazy 8. And that number, of course, represents infinity, which is not a number. As you may imagine, there are footnotes to many things that I will be saying, but that is fully accepted, reasonably fully accepted, that infinity is not a number. But it is treated as if it were a number because we do need a symbol for infinity. The reason it's not a number is because you cannot measure it. That's the ultimately distinctive aspect of infinity, whether you consider it a number or not. It's representing a quantity to the same proportion that linear spatial separation indicates a quantity, which is called distance. That is the quantity. But all it is a separation on a line, which you can then metricize with hatches. And if they're all the same, the smallest, if they're all the same, then one of them is called the index. That's the index of the metric of the object in that space. Now, that's 4 levels of definition, but I am being enormously precise because I'm leading you to something of a shock. And in order for you to be shocked appropriately, this will be good. You'll be pleasantly shocked, because we now need to define what is a number. And that is rather easily done based on what I just told you, because this is in fact how numbers were developed. When Euclid defined the line, he defined it according to the fact that it must consist of points. And retroactively, that is an inassailable statement, but it is axiomatic. In other words, it can't be proved. And that's an axiom. There's a footnote, because you might try to force a proof. But actually, the way science begins in any system, in this case geometry, in this case with Euclid, if you say that the point has no dimension, that's an axiomatic statement for obvious reasons. The damn thing doesn't even exist. So you're expectant of further statements. And the way sequential logic is used, it's impossible to absolutely begin. And that's been proved. It's actually, I believe it can be proved that that is a variation of Kurt Gödel's incompleteness theorem. But I don't have time to delve into that right now. The point being, and always pardon the pun on point, that is not a confusing issue that point has two meanings here, but it has more than even those two meanings. Point being more or less a metaphor, the way we use it, get to the point, or the point being, it's the exact same word, it's a homonym, with that Euclidean object which has no dimension. So the point has no dimension, but that actually makes sense once you know what is the line. And that's the second sentence in Elements, is that a line has one dimension. Now, if you want to parameterize the line, that is the application of a metric. And if you decide on your metric, which seems pretty obvious to us, but it's important to say this out loud, you want to have a separation between 2 points. And that's an extension of the word point, because now you have 2 points, but they're different points. What's in common between the points is the line. And so what you want is the line, not the points. The points have no dimension, but they form the end points of the line. And with that, you have a line segment, and that is distance. That builds pyramids, that lays out plots of land so people know where their boundaries are. It has enormous applications that I don't need to go into. But that is called a one-component number system. Because when you start at the origin point, which is where you're measuring from, you do have to give that a symbolic number in order to have an index, which will be 1, which is defined as the lowest counter. And that's fully accepted. I know this may seem a little tedious, but it's extremely important, and you'll see why quickly. Very quick, more quickly than you may like. This goes very deep, very fast. I am here to make this a cakewalk, whatever that means. I may have heard what is a cakewalk once, but I don't think so, because I would have remembered it, because whatever it is, it's surprising. Because what in the world is a cakewalk? Well, if you know, leave a comment. That'd be beneficial to all viewers. So this is going to be very simple, but it has never been simple in the past. I'm a master of making things simple. It's one of the great blessings of preferring geometry over mathematics. Mathematics is not nearly as useful to a full-grown man in the long run. Mathematics is not the best tool if you had to choose one out of mathematics or geometry. You must select geometry. That's the only way to begin. You may know that a lot of men would disagree with what I just said. Oh my God, no, Scott. Numbers are everything. Well, I'm not going to go into that, but I'm fully aware of that side. as you can well imagine. If you're not, don't worry about it. But I'm just telling you from the point of view of someone who has mastered the subject. Geometry is the way to get at mathematics, and I'm going to be showing that to you, but it is going to blow your mind at more than one place. So this is science at its best, for several reasons, but you're going to have to trust me. I hope you do. I've spent 4 years making 1,260 videos simply to practice to do what I'm doing now for you. This is for you. You don't owe me anything and never will. This is for all of science. So, when you begin the way Euclid did with 0D, we can now say, certainly as of the 20th century, I'll just put it that way, that is linear 0. The reason we have to have 0, which is a peculiar number because it's not there either, it's no quantity, which matches the point, which has no anything. It's not even there. But if you say that it's a position in space, in this case, physical space, you make a point in physical space, that's the beginning of your string that you use to measure to cut some block for your pyramid or to lay out some land tract, which has to go on record with the governor, so nobody is in any doubt about how long is that line that marks the boundary between your property and somebody else's property. A distinctly civilized notion, which some tribes of the earth have had no conception of. They don't understand that you can divide up land with imaginary lines. They are imaginary, but they correspond exactly to physical reality, to the threshold that is needed for the job. Okay? This goes all the way to engineering tolerances. So, we do have the beginning of a number system based on distance, and now we know that the point is 0, but that's only half a statement, because the purpose of this geometric construction is to make measurements. And that's actually tautological. And that's the service of numbers. They validate a geometry. In this case, what is considered to be the simplest geometry possible, I would have to agree that for 2,500 years, it has been the only geometry ever used. And Lobachevsky and Bolyai did not change that. They added nothing to that. They simply extended linear geometry in a very interesting way. By disregarding the parallel postulate, they were able to develop a curvature geometry, and they did it at the same time and they did it independently. And when Bolyai contacted Gauss through his father, who was good friends with Gauss, they communicated over quite a long distance, but I guess they had a mail service or however they did this. And Gauss claimed, oh yes, well you just discovered what I already knew. Nobody to this day knows if Gauss was just lying. And the only way to determine if he was lying would be based on his reputation, because nobody ever found any really anywhere near conclusive notes to confirm that he actually had discovered what's called, it's one of two it's given a name, but there are two of them. It used to be called Lobachevskian geometry, but you have to be more specific. The modern terms for the two non-parallel postulate obeying geometries is elliptical geometry and hyperbolic geometry. And that's reasonable, but I'm not going to go into that because all of that is an extension of linear geometry, because you're still using one component numbers and you're still computing simple distance. There's no change in what is desired. You're trying to measure distance. Okay, Well, it's very important to be obvious here because of what's about to happen next. So it turns out we can go back and say of Euclid that he parameterized the plane with two lines. Well, you can see right away that that's actually two different measurements. That's true. And by doing so, by measuring on the what is now called the x-axis, but that was actually a late development called the Cartesian grid, whereby René Descartes, drew the y and x-axis. He actually invented that, and that's another case of a simultaneous discovery. He wasn't the only one who discovered that, and it was at the same time because neither man knew of the other's work. So it's virtually simultaneous, and it's remarkable how many times this happens. So we already have two examples of that in our simple sequence to understand what is geometry and numbers, and what do I have to say about it that's so magnificently important. Well, if you have single component numbers, which you do on the line, you begin with 1 and the next hatch is 2. And then you can count up as high as you like. And you remember that phrase from your calculus textbooks. Every calculus textbook has this phrase. You can count up as high as you like. And that's a direct reference to infinity. And there are two forms of infinity, and they were simultaneously discovered. A third case of a simultaneous discovery by Sir Isaac Newton in England. Actually, he was trying to get away from the Black Plague, so he was in an interesting part of England where he had a good time, but he didn't really do much else except work on his science, because that's all Sir Isaac really did. But in Europe, Gottfried Wilhelm Leibniz also discovered the calculus, and with a different emphasis. And that does make sense, although historians have rather argued about this, but to just treat it logically, now that we know what they did, is both of them simultaneously discovered two operations that can be conducted on the plane. And it's remarkable what they discovered, because it can be extended, what they learned to do on the plane, that can be extended to any dimension. And that's called the calculus, of which there are two. And they're reciprocal, but that's not precise. We don't have a word for the invertibility of the infinitesimal calculus, called the derivative. It could be called the derivative system, which is considered to be exactly the opposite of the integral. And if you've studied calculus, you already know this, but again, it helps to just spell this out. And I know exactly what Leibniz and Newton did, but I've never heard anybody state it correctly, ever. And I've canvassed at least 24 textbooks just to see how they define the calculus. There is actually something called the law of the calculus, which simply says that the derivative is the inverse of the integral, which is not true. That cannot be proved. Although it's treated as if it were true, because the whole nature of the calculus is you get an approximation. So it's not geometry. It's not geometrically correct. And there's a reason for that, which you're going to see. This is going to just shock the shit out of you, because this actually explains the calculus for the very first time, and the reason why it doesn't work, and the solution that makes it work. And I would have to say that that is a grandiose and perhaps preposterous statement. But I'm preparing you. I hope you listen, because this is going to be very interesting. What you see, it's so simple that it's bafflingly simple. You won't be able to believe what you're able to see once you fully understand the basis of what is a number, and what is an object, and what is a space. What is a parametric? That's the application of a number system to a space. So we begin with a line, and that has all the numbers. That has been known ever since the time of Euclid, essentially. The Indian mathematicians worked on this extensively, and so did the Arab mathematicians, and they were able to draw similar conclusions, later confirmed in Europe. The Europeans were all about mathematics for centuries, as you may be aware if you're a fan of mathematics history, which is well worth studying. It's something else, but it's really involving. I mean, you might do that for the rest of your life and in a sense never get anywhere. Oh no, you'll get somewhere because you're studying people who study rational logic in some way. But the nature of the number system that we use is entirely based on Euclid. It's just that it makes such perfect sense that nobody questions why it works or how it works. It just works. Well, we're going to be a little more specific than that since we have to talk about it. That's the main reason for getting definitions precise in this form of formal science, which I'm presenting a proof sequence to you. And we'll go back over it so you can see the separate steps of the proof. But for now, I'm just describing the ball game, the playing field. What are the rules? We have the bases, we have the players, we have the bat and ball, whatever. This is way simple, though. All we have is a plane, which is infinite. And that's actually a problem. However, it never stopped anybody. Nobody ever cared. Although it was known for centuries that infinity is a real bitch. And you really have to be cautious with infinity. And we're not going to talk about that directly because I solved that problem, and I'm the first man to solve the problem of the plague of infinities. If you know anything about the history of the study of infinity, you know that there are countless books written about it, and it is still the hottest topic in town. Because infinities tend to destroy your calculations. And that's been true certainly in cosmology and even in the geometry of the supermassive black hole. There is an infinity involved. And you already know that the universe is spatially infinite, which nobody has ever solved. Nobody knows what even to say about the edge of the universe. Although there is a theory, a very interesting model, which I'll show you what it means. It's very important to know what that model means. So, this does go right away to the highest level of physics, to the cutting edge, where men are baffled and have no idea how to continue. That's basically quantum mechanics and cosmology, but also extending to astrophysics and deep space, because we don't really know much about the geometry of galaxies because of dark matter, and clusters of galaxies, which are the building block of the universe, because everything is made of clusters of galaxies. I don't know if you were aware of that. That's not perfectly true because there's a very special object called the quasar, which breaks all the rules, and science has no idea what those things are. I do, and I'll show you what a quasar is. It's strongly related to the supermassive black hole, which just coincidentally is always at the center of any galaxy. And more can be said on the supermassive black hole, but the characteristic attributed to the supermassive black hole is that it has infinite density. And that produces what is called a singularity, producing an event horizon using that form of mathematics, the Schwarzschild radius, and it's even gone to where even Sir Roger Penrose, in collaboration with the late Stephen Hawking, worked on everything there is to know about supermassive black hole geometry. They were the masters, where some of the theories that have come out of that, which are now considered to be perfectly tenable, are based on this infinity, which is always a problem. And so the supermassive black hole cannot particularly be taken into a laboratory and studied to see if it actually does have an infinity in it. But it is presumed that it does. Also, the universe itself comes from an infinity, and it is considered to be expanding into another infinity, which is anti-physical, so that's a very interesting model. It has gained prevalence, as I'm sure you're aware, since you're not allowed not to know it. The United States government enforces that against a knife against your throat. Yes, it is expanding, and nobody will ever question that. In real science, you question everything. Doesn't make any difference what the United States government says. But that's where we're going, And we're also going to the quantum limit, which is, as I'll show you, the reciprocal of the spatial infinity going out, which nobody can define or even address. It makes no sense. It just ruins everything. So the plane has an infinity. How many infinities does the plane have? It depends on if you begin with Euclid or not. If you begin with Euclid, who began in the plane, because everybody has to begin in the plane. You know why? That's how we see. That's actually how we think. That is, its consciousness is a plane, although it's superpositional, and that's the most profound statement I've made thus far this evening. So to get back on track now, that you have the bracketing information so you know where this is going, why this is so critical, you begin with the plane. How many infinities does it have? I think you might say 1, you might say 4, because when you draw the two lines that fill the plane, it fills it with a grid, because you can use the metric on this line to have parallel lines, and then the metric on this line is perpendicular to the other metric, so you have squares. And that's exactly what is done to this day. That's how Einstein did it. You begin by squaring the plane. That's why we have so many squared numbers, is because the plane, which is infinite, is parameterized with squares. But if you break it down to the two base axes, that simplifies the whole matter. Now you don't have your plane filled up with squares going to infinity. Instead, you just have the two lines that go to infinity. How many infinities does a line go to? You could either say 0, 1, or 2. If you say 0, it's Lobachevskian. It's non-parallel postulate geometry. And there are two ways to actually extend that. We're not going to do that because that's incorrect. And that's why their geometries are not used for anything. And you can check that. It's a dead end. It's quite interesting, though, because it's a direct address on the parallel postulate, which it violates because lines are not parallel, but they can be non-parallel in two opposite ways. So that is not non-Euclidean geometry. What would be a non-Euclidean geometry? I'll show you, but you won't find this anywhere. I'm going to be the first man to tell you this, and nobody knows this, but I'm going to make it obvious. If you begin with a plane, which you can't begin with volume space, and you can't really begin with a line because it's not a legitimate space, because it's lacking a visual dimension. A line by itself cannot be seen because it's just made with points. Although this comes to a philosophical issue, which I definitely don't want to get into, but you should be aware, there's various ways of looking at this. Because we're at the axiomatic basis and you can't define anything clearly. You simply have to make statements that you can support later. So the plane is not a line, but there's a relationship between the line and the plane. So that if you begin the way Euclid began, you begin with a line in order to make a plane. So you begin with a line which will come to have a metric that is obvious. This line will have a 0 at the center, so that this direction is positive and this direction is negative. Euclid had no concept of that. That's very important. He didn't deal with numbers, numerics, and that sort of thing. He knew about the metric. He knew this was all measurements. But the Greeks, including Euclid, thought strictly in terms of geometry. And that theorem, called the Pythagorean theorem, which is simply the right angle law for the plane, or the right angle law for lines, which is synonymous, is adding two squares to make another square, which may strike you as insane. It is. When you add two squares to make another square, on a right angle, you can prove the length of the hypotenuse, which gives you access to the space in between the lines enclosing a square space. If you have that grid metricized on an index, such as 1, which you have to do, that has been proved, whether it's the Planck length or something else, you have to have a finite distance to have an index for your metric, which in this case is distance. But you see on the plane, you're not measuring distance any longer. In a subspace, you're measuring distance, because the line is a subspace of the plane. All of this has been proved. Just take my word for this if you're not certain. But leave a comment if you want further explanation, because now's the time to ask questions. But now that you have the metric for distance, you can draw a line, for instance, on a blackboard, or for instance here. Well, actually here, you see that D is a line, but it's not infinite. It's inside a circle. And in fact, it's the diameter, which is the longest line you can draw. And it bisects the circle. All of this is familiar. But it's very interesting to look at the relationship between that line segment, which is a distance because it has two endpoints. For now, we're not going to deal with infinity. That's simply an extrapolation into imaginary space. And I've proved that that's the correct definition of imaginary space. It's exactly the same thing as infinite space seen from one angle. Very important to add that. Seen from one angle. All right, so we're not going to deal with infinity yet, but we're getting to it quickly. And again, if this doesn't blow your socks off, you should be a poet instead of a scientist. I'll just put it that way, rather crudely. This will blow your socks off, so prepare yourself. That line is embedded in a space, and the space is bounded by the circle. Correct? So that is an object in the plane, inside of which is the line. Does that sound reasonable? Because I proved this, so I hope you see that. I proved much more than that. But the diameter of a circle is an oriented line segment. And it fully exposes the beauty of distance, that you can measure that. Now, if you give it a number, which is called algebra, it's the beginning of algebra, you kind of reverse things and you say, okay, we have that line, let's just give it a number and see what we can do with it. Because we can define that number perfectly according to Euclid. We're going to say that that diameter is 1. And that's the distance. In this case, there's no 0. You see that? Which may not make sense to you, because you see that it does have a center. But there's nothing that says that that center has to have a numeric value. A specific numeric value. If you say that that's a line segment, it's just interesting that it goes through the center. But if you draw that red line, which is the radius, and you say that that is 1, that's actually from the center to the edge. And that turns out to be the right way to do it. The Greeks did not use the radius. Although they did, they knew of it. They much preferred the diameter, for reasons I won't go into, and you should verify that because I'm not entirely correct. But there are two different ways to draw the most simple line inside a circle, which is a space. How do I know that the circle makes a space? Because there's something inside. Well, what would you call what's inside the circle? That's a geometric space that's inside the circle. Well, you might ask, well, what about outside the circle? Very good. Is that the same space? It might be, but not necessarily. So this circle is not necessarily being drawn in physical space. Now you can see that, at least in these projections, they are drawn in some kind of physical space because you're looking at it. That's very important insight. In order to use a geometric object, you have to see it. Otherwise, it's not an object. And that has a footnote. But all of this at this level is quite clear and obvious, and it's the right way to do things. I have studied this out more than once. So there is a center to a circle, though. But we're not going to say that it's a point. We're just going to say that every circle has a center. You could also invert that. For any point in the plane, you can define a circle. So if you do begin with Euclid and say that the point has no dimension, you don't have to draw a line. You can draw a circle. And that's very interesting, because take a look here at my fingers. They're all at that point. And now here's one line that comes out. One line. It's a different line, isn't it? It's a line that goes in all directions at once. Well, on the plane, it goes out in all directions at once to make a circle. And that's the definition of the radius. It's one possible definition of the radius. It is the line which, if you draw it from the center in all directions at once, makes a circle. Can you draw a line in all directions at once? You can't, you cannot, but nature can. Nature does it all the time. And we won't go into physics yet, but this is going directly into physics. So, the circle is an object in the plane. Can we attach numbers to it? That's called can we parameterize the circle so that we can put numbers on it? If you look at the circle, you see it has no beginning and end. That's called continuity, by the way. So it's continuous. It's non-quantizable. It can't be quantized. There's no way to quantize the circle. But you can try. And of course, this has been tried, as you're well aware. The way the Greeks did it is they used that diameter, which is the longest line that can be drawn in a circle. And what it does is it makes a bipolar point. And that bipolar point is uniform. No matter how you rotate that line, it will always bisect the circle, which means it's making 2 points on the line. 2 points. That's quite significant. Are those Euclidean points? You might try to say so. What if you did? Well then, on that line, if you say that the diameter is 1, then you can arbitrarily select one of the two antipodes, which are the 2 points at the ends of the diameter, and say that that's 0, so that you can measure a distance. But you can see you could be measuring the distance in either of 2 bilinear directions. So which is 0? Well, you can solve that problem by drawing a radius instead, and that's that little red line, as I think you can see. If you do that, then the center can be said to be 0, because you're drawing a line from a point. And the point is there because it's the center of the circle. You may be starting to get a little bit, there may be a little flag waving. Is that the same point? Don't answer that. I just want you to know what we're approaching. That point is defined as the center of a circle. Okay. Is it a Euclidean point? We'll leave that unanswered. We're just going to say, sure, yes. So it has a value of 0. Well, you can see that you can prove that, actually, because that's the same point through which the diameter goes, and it bisects the diameter. So when you draw a radius from that same point, it's going to have a value of half the diameter. But now you have a 0. If you make the center 0, which of course you would, because now you can get a distance from the center point to the surface, and that implies a direction. When Euclid put his line in the plane, it's a non-oriented line. It does not have any direction. Although you could say it could be any direction. He could draw it straight up and down. He could draw it at any angle. You could say that. And you should. So which is it? Does it have a direction or not? The radius does. And the reason you can say that the radius has a direction is because you can see in which direction it might point to get to the same circle. So it's not arbitrary, you're actually dialing another point on the circle. So you can use that line as a what? You're making a distance from the center to the surface. The unit circle, which is virtually worshipped, I will simply say it that way, I certainly virtually worshipped it at one time. The unit circle is defined as a circle with radius 1, which defines the center as 0, and it defines that point on the surface to be a linear distance of 1. For convenience, you can say that that has a direction on the x-axis, and that's how we've always done it. You've done it, we've all done it. So that radius is always from 0, x. Do you see a problem there? You should. You're only measuring in one dimension. That is an oriented line now. It's, you could say, horizontal. And you're going in the positive direction. So you're going from 0, from left to right, 1 unit of linear distance. So that is both, that is called the index number, because 1 is the smallest counting number, and you need a counter. We just went through that. So there's nothing smaller than that. That distance is 1. By definition, there is no distance less than that. Indeed, you can see that there could be a distance less than that only if you say that there are numbers less than 1. Well, we do. There are numbers such as 1/2, 1/4, 1/8, and that goes infinitely towards the center, or towards the edge, depending on how you're doing it. Zeno's paradox is based on the attempt to go from the surface to the center in halves, because it's the simplest way to demonstrate Zeno's paradox, that if you jump halfway, and all you do is jump halfway again, you'll never reach the center. So that's an infinity of halfway jumps. That's called Zeno's paradox. And now you're going to see the solution to Zeno's paradox, so it will never be a paradox again, and this will introduce you to the realm of modern physics. That's an hour. I need to eat. I will be back later this evening. It is still the 28th, but it's now sunset. I'm anxious to get all of this out, but I estimate it's going to take about 4 hours to go through the basics, another 4 hours to explain the immediate impact on physics and mathematics, and then another 4 hours to describe cutting-edge upper-level physics, conundrums, impossible solution, nobody can find solutions, such as Einstein's field solution. We'll get that. The collapse of the wave function, we'll get that. We'll explain superposition so you can see it. We'll explain entanglement for the first time. We're going to get the quantum of gravity. We're going to redefine the atom so it makes geometric sense. We're going to abandon the standard model of particle physics. We're going to abandon the cosmological model. We're going to find out the right solutions so we no longer need to rely on Big Bang expanding universe modeling because it's wrong, and now that can be proved. And I'll show you much better the correct answer. And that will describe a lot of things in astrophysics, including dark matter, which nobody knows what it is, as you well know. We'll be able to dispense with the whole cosmological model that invokes such strange concepts as dark energy, which is a linear infinity, and it will never be rationalized. There's no way, it's a dead end. That's why they're making no progress. They've made no progress for a century in cosmology. None. I have the breakthrough for that. Also, quantum mechanics is completely not understood. And everybody admits that. It's as if everybody has given up. No, that has a very, very rational solution which unlocks subatomic physics. I'll show you the structure of all the elementary particles. There are exactly 2 or 3. And we'll explain that later. That's an hour. Thank you so much for tuning in. It very much impacts me to know that I have viewers. Currently I have between 5 and 10 on a regular basis. They may not be the same people. That's paltry after a 3.5-year effort. I've expressed my bitterness, my anger, my rage. I've made all kinds of threats. I've done everything I could to get someone to assist me to get an interview. I've done my best. I'm not going to do more than I have, and so I'm reaching out. But the fact that you are viewing is really all I ask, because I don't have faith in human beings anymore. All the interviewers on YouTube are after money. They couldn't care less about truth. And so they'll never find out about me. If you want to blame that on an evil spirit, I certainly do. And now you know a lot about your professor. But if you want the answers, I've got them, so stay tuned. Thank you. We'll be right back. Keep looking up.